Bismillahirrahmanirrahim. Alhamdulillahirabbil wassalatu wassalamu ala asyrafil anbiya'i wa mursalin wa ala alihi wa sahbihi ajmain. Assalamualaikum warahmatullahi wabarakatuh. Okay, in this session, in this video, I would like to discuss one beam question. Beam question. This is actually pre-assignment question. Okay, I want to consider beam with support settlement. Okay, beam with support settlement means that we have to consider FEM due to external loading as well as FEM due to delta, which is vertical displacement since beam is a horizontal member in one table, since delta is given in the question and external loading also given in the question. Okay, so let's consider one beam question, beam with one beam, let's say one beam. Let's say this is the beam. So this beam I want to put as 3 span. Okay, 3 span, one fixed support. Okay, this is one fixed support at D. Okay, fixed support at D. Okay, fixed support at D and has roller or pin support at A. Okay, A, B, C, and D. Okay, so this is pin, and pin. Okay, so this is a continuous beam. This is a continuous beam, and okay, this is the distance between A to B, A to B, B to C, and C to D. Okay, if you have any question, you can write your question in the chat box. Okay, so this is A. A is pin, B, C, and D is fixed. D is fixed. So okay, length of AB, for example, this is 4 meter. B to C is 5 meter. 5 meter, and C to D is 3 meter. Okay, 4, 5, and 3 meter. So along member BC, okay, there is UDL on member BC, along member BC, and this UDL has 30 kilonewton per meter. Okay, magnitude 30 kilonewton per meter along member BC. So let's say EI is not constant. So this is EI. Okay, B to C is 2 EI. And C to D is EI. Okay. So this is the question. Member AB. Member AB has no load. Okay, we have member BC with UDL of magnitude 30 kN per meter along the member. And we have EI, we have CD with EI. And there is no loading on the member. Okay, so the question is we need to calculate member and moment. The question is calculate member Okay, calculate member and moment. Member and moment. Okay, calculate member and moments. Okay. Okay, by considering support settlement at B, okay, of magnitude 35 mm. Okay, support settlement downward. Okay, settlement means downward. Calculate member and moment by considering support settlement at B of magnitude 35 mm. 35 mm. Then draw shear force diagram and bending moment diagram. Okay, draw shear force diagram and bending moment diagram. Okay, so by having this support settlement means that there is a delta at position B, which is equivalent to 0.035 meter. Okay, 0.035 meter. Okay, so always remember that FEM. We have to, okay, FEM has actually the effect that is not only due to external loading but also due to delta, and FEM is behavior. Okay, so by looking at the external loading, so we will have due to external loading, okay, so we can calculate FEM for member BC. So it is FEM. So FEM for member BC, it is like this. It is 30 and 5. So the moment, okay, will because of the loading, it will be bent, okay, and we have to apply moment so that the moment will push back both end to straight position. So we have to apply moment in opposite direction like this. Okay, opposite direction like this, and the formula is WL squared over 12. It is WL squared over 12. This is WL squared over 12. WL squared over 12. Okay, so FEM, so in this case, this is actually B and this is C. Okay, B and C. So the formula is WL squared over 12. Okay, for both, because UDL subjected along the member. Okay, along the member. So this is the formula as given in appendix. Okay, this is the formula. Okay, so what we need to do is, due to this is actually FEM formula considering external loading. So So we have to calculate the value. So it is FEM. Okay, FEMBC. FEMBC. Okay, since the sign convention for MDM, okay, is clockwise, positive, clockwise. So FEM at B, since the behavior, okay, is in counterclockwise and it is opposite with clockwise, so it is negative. So we have to put negative. So W is 30, L is 5 square, divide by length. Okay, divide by WL square over, no, not divide by length, WL square divide by 12. Okay, divide by 12, so what do we get? So we get, okay, WL squared over 12. Okay, open the calculator first. Okay, let's open the calculator. So it is 30. Why I get 2? I want to close 1. Okay, open again. Okay, so use calculator to calculate. Okay, it is 30 times 25 divide by 12. WL squared over 12, so it is 62.5, negative 62.5 kilonewton meter. So we will get FEM CB is positive value. Okay, because this moment when react to the loading, okay, we have to apply the moment in clockwise direction because it is represent the behavior. Okay, the behavior, so it is positive, same value, so same value we get positive 62.5 kilonewton meter. Okay, this is due to settlement. This is due to external loading. Now we move to settlement, due to support settlement. Okay, 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 what we need to do is we need to, number 1, okay, we have to sketch the free body diagram due to support settlement. Okay, draw the free body diagram. So this is the beam. Okay, this beam has A, B, C, and D. And settlement occur at position B. Settlement occur at position B. Okay, settlement occur at position B. So we have to, okay, to draw the triangular representing delta, and delta is vertical perpendicular with element. And of course, whenever we deal with delta, we may have the triangular. Okay, so B only displaced, B only settled. So A and C A is pin support, C is pin support. So A and C, point A and point C remain at same position. So we have two triangular, okay, like this. We have two triangular like this. We have two triangular like this. Okay, we have triangular for AB and we have triangular for BC. And delta is this. Delta B equal to 35. Delta B equal to 35 or 0.035 meter. It is 0.035. Okay, 0.035 meter. Okay, so the triangular, okay, the beam after side sway, so AB is this. Okay, we have to apply the principle, the concept whenever the beam, okay, the beam settle, we have to look at to the new position, which is inclined member right now, okay, as shown here. And remember that beam is always horizontal, means that the reference line is a horizontal line. So we have to, okay, I want to draw the horizontal line here, represent the reference line. Okay, reference line or the, okay, the beam, the original beam position. And in the triangular, of course, this triangular must have this. It is perpendicular. Length for AB is it, okay, it is 4 meter. Okay, this is 4 meter. Okay, 4 meter. And delta is 0.035. This is delta. Okay, delta B. Okay, delta B. And with between L, AB and delta is perpendicular. Okay, so remember that same to what I have, okay, I have actually explained in frame. Column is vertical member, the delta is horizontal, it must be perpendicular, so we have to identify where is the triangular. Okay, and the behavior, okay, the behavior we measure from the angle, actually the angle we measure from original position to new position. We measure the angle because the easiest way to identify the FEM sign, okay, behavior belong to FEM, the FEM sign, okay, will be easily okay, after we determine the delta. Okay, because I have also tell in my previous video that between angle from original position to new position, between angle and FEM, it must be opposite. Okay, so the angle, okay, is measured like this. So from original or from reference line, okay, it is just like this. Okay, this is just like mathematical when you learn about angle, sudut. Okay, the angle is positive. Okay, the angle is positive. What can we conclude when angle is positive? When angle is positive, FEM is negative. Why FEM is negative? Because this is the line. Okay, this is the line. And moment will push back this okay, this beam after settlement to its original position. Okay, the moment will push this to straight position, to horizontal position, means that we have to apply moment. We have to apply moment. Okay, we have to apply moment to push this back to top, and this will follow. So this is FEM. So this is FEM direction. And see, so between angle here, this is representing angle. Angle is positive. FEM is negative. Okay, so this is FEM. This is FEM. This is FEM. FEM. Okay, FEM. This is how we analyze or we understand about the FEM due to delta, due to settlement. Okay, so for AB, if the angle is positive, FEM is negative. Okay, FEM is negative. FEM is negative, so this is the angle. This is the angle. Okay, chord rotation. Okay, this is the angle. Angle is positive, FEM is negative. Angle is positive, FEM is negative. So when we apply formula to calculate FEM for AB, okay, we have to have FEM negative. We have to have FEM negative, so we have to put negative in the formula because it represents behavior. It represents behavior. So FEM for AB, and for settlement for delta, FEM AB will be equal to FEM BA. Okay, FEM BA, and this is equal to, okay, we want negative FEM. We want negative FEM because the behavior is negative. Okay, so we have to put negative. We have to put negative. The formula is 6 EI. 6 EI. Is it EI or 2 EI? Okay, it is EI. 6 EI delta. So this is delta B. Okay, delta B divide by L squared. L is 4 meter. It is 4 squared. And this is equal to, okay, this is equal to, so in FEM, in beam analysis, whenever settlement is given, so we should have EI value so that we will get FEM. Okay, FEM, not in terms of EI but the value, because this value will be sum. Okay, we total the FEM due to this effect plus FEM due to external loading just now. Okay, this is FEM. So let's say E is given as 200 GPa and I is given as 500. Okay, 500 times 10. 6 kilo, meter 4. So this is meter 4. Okay, meter 4. So we simplify this first. So EI, okay, EI is equal to 200 times 10 power of 6 kilopascal. Kilopascal because Pascal itself is Newton per meter square. Newton per meter square. So it is 200 times 6. Okay, times 10 power of 6, it is kilo Newton. Okay, kilo Newton per meter square. Times 500. Okay, 500. Okay, I want to continue. Okay, it is 500. Okay, so this is millimeter 4 normally. Okay, like this. Okay, it is 500 times 10 power of 6, and millimeter 4 is negative 3 times 4, it is 10 negative 12. So we get meter 4. So what we get is it is equal to 200 times 500. 200 times 500. Okay, 500 kilo Newton meter 2. Because, okay, 6 okay, 10 power of 6, 10 power of 6, 10 power of 12. Okay, 10 power of 12, 10 power of negative 12. It is 10 power of 0 equivalent to 1. Okay, kilonewton, remain kilonewton per meter square times meter 4. So we get meter 2. So kilonewton meter square. This is the unit for EI. It is 200 times 500. 200 times 500 kilonewton meter square. So this value we need to substitute into the FEM formula to calculate FEM for AB and BA. Okay, so we substitute the value. So it is 6 negative 6, E is 200, I is 500 times delta is 0.035. Okay, 0.035 because we have put negative in the formula. So divide by 30, 4 by 4 square is 16. Okay, it is 16. So what we get is FEM AB equal to FEM BA equal to negative, it is negative 6 times 200 times 500 times 0.035 divided by 16. Okay, 6 EI delta, 6 EI delta over, okay, it is 6 times 200 times 500 times 0.035, okay, divided by 16. So we get 1312.5. This is kilonewton meter. 1312.5 kilonewton meter. It is negative. Representing behavior, this behavior. Representing this behavior. It must be negative representing this behavior. This is negative FEM. So we should get negative FEM. Negative FEM. Okay, so this is for AB. So when we move to BC, again BC also, okay, perpendicular. BC, okay, perpendicular like this. So the length of member BC is 5 meter. The length of member BC is 5 meter. And don't forget BC is 2 EI. BC is 2 EI. So BC is look like this. Okay, this is BC. Okay, the reference line is horizontal. The reference line is horizontal, representing the original position of beam, and we will measure the angle from original position. We measure the angle from original position. So this is original, so it is negative. So this is angle, okay, called rotation, and this is, okay, this is negative. Okay, this is negative direction. Okay, negative. negative direction. Okay, negative direction. And FEM, so for FEM, so this is for FEM. FEM, we must apply moment to counter back the beam after settlement to its original position, means that it is a horizontal position. So when we apply moment, we need to apply moment, okay, so that the beam will move back to its original position. Okay, and the easiest way is by looking at the angle. If the angle is negative, FEM is positive. So FEM is positive. Okay, FEM is positive. FEM is positive. Okay, FEM is positive. So FEM is positive. So this is positive value. So this represent positive. Okay, positive FEM. This is positive FEM. Okay, positive FEM. So when we want to calculate FEM due to delta for member BC, so this is BC, so we have to apply formula. So we have to apply formula. This is for BC, so let's label. Okay, this is B and C. Okay, this is B and C. Okay, this is member BC. Okay, for member BC, it is FEM. It is FEM for BC, which is equivalent to FEM for CB. And this is FEM is positive, so we put positive. Okay, FEM is positive. Then we apply formula. Then we apply formula 6. Okay, 6 EI. 6 EI. Okay, 6 EI. Okay, delta B. This is the formula. Okay, delta B over LBC. Over LBC. LBC square. Okay, so it is 6 times 2 because BC has 2 EI. So it is 6 times 2 times 200 times 500. Okay, it is 500 times 0.035 divided by 5 square. Okay, divide by 5 square, so we will get, okay, FEMBC, FEMCB, S, okay, S. Okay, calculate this value. This is 6 times 2 times 200 times 500 times 0.035 divided by 25. So we get 1 positive 1680. 1680 kilonewton meter. Okay, so we combine FEM. So now we want to combine FEM. Okay, we combine FEM. So we have FEM for AB. FEM for AB. Okay, from external loading, no, 0. FEM AB due to settlement. FEM AB is negative 1312.5. Okay, it is the negative plus negative 1312.5. So we get negative 1312.5 kilonewton meter. Okay, FEM BA. Okay, FEM BA. From external loading 0. From external loading 0. For BA, BA also we get the same. Negative 1312.5 equal to negative 1312.5 kilonewton meter. Okay, then for FEM BC. Okay, FEM BC. So look at to the FEM due to external loading due to W, we get FEM BC is negative 62.5. Negative 62.5. So is negative 62.5. 2.5. Okay, we have to plus with FEM for BC. FEM for BC we get positive 1680. 1680. So this one we get negative 62.5 plus 1680. So we get 1617.5 kilonewton meter. And we continue calculate FEM for CB. FEM for CB, this is equal to positive 62.5. Okay, we have to plus with 1680. Okay, we get 62.5 plus 1680. We get 1742.5 kilonewton. Okay, kilonewton. This is FEMCB. And there is no value for FEMCD and FEMDC. So we only have value of FEN which come from member AB and member BC. Okay, in member, okay, by looking at the diagram previously, so okay, UDL or external loading, okay, is only applied along member BC. There's no external loading along member CD. So FEM due to external loading for member CD is equivalent to 0, and due to support settlement, CD does not get affected because okay, B is settled, C is remain at same position. So CD will remain zero displacement. Okay, zero displacement. So we have FEM after we combine FEM due to external loading and due to delta. So we get this 4 value. Okay, we have this 4 value. Okay, so for FEM in this this FEM, I assume that both end is fixed. So we will do modification in the table because NA is spin. NA is spin and the final moment at A must be 0. Okay, please see how I made modification in the table in order to get back 0 moment at support A. Okay, so we move to table. Straight away move to table. So in the table we have 6. We will have 6 end moment because we have that 3 members. 3 members means that one element or one member has to end. So now we have 3 members. 3 members means we have 6 member end moment. 6 member end moment. So So we have to have A, have here AB, and then B A, and then B C, and then C B, and then C D, and then D C. Okay, 6 members, 6 member, and then okay. Okay, so okay, separator for each member. Okay, ABBA. So we have okay BCCB, and then CDDC, CDDC. Okay. Okay. So in this table, I want to calculate. I want to actually put K and DF directly in the table. So doesn't matter. We have to know that the moment that we distribute is actually the joint moment we calculate by finding the moment times with distribution factor. Okay, so what we want is distribution factor. And the first member and moment in the table is this moment that we have calculated. So we need to have distribution factor. And distribution factor we calculate from stiffness factor. So now I want to put K in this table. K in this table. K in this table. Okay. In this table. So DF. Okay. For member AB, K is equal to 3EI over L. Because the stiffness factor, we must consider the end condition. End condition A is spin. Okay, A is spin. So for K value, we need to consider end condition, and for end pin it is 3EI. It is 3EI over 4. It is 3EI over 4. It is 0.775. Okay, so this is 0.75. This is 0.75 EI. Okay, for BC, since BC has 2 EI and it is internal support, so we need to use 4 EI. It is 4 times 2. 4 times 2 divided by 5. 4 times 2 divided by 5. 4 times 2 is 8. Okay, 8 divided by 5. 8 divided by 5, so we get 1.6. It is 1.6. Is 1.6 EI. 1.6 EI. Okay, CD, member CD. Okay, CD is 3 meter. CD is 3 meter. And the formula, because D is fixed, N is fixed, far and fixed, we use K is equivalent to 4 EI over L. It is 4 divided by 3. 4 divided by 3 is 1.3333. Okay, 1.3333. So that is K value. Okay, 1.3333 EI. 1.3333 EI. Okay, I have put EI here because K is in terms of EI. So I put EI here. So it is 1.3333 3, 3. Okay, using this value, we will calculate distribution factor. And the distribution factor, remember that A is pin, and pin, the DF is equivalent to 1. So this is 1. Okay, and D is fixed, and the distribution factor for fixed end is 0. So this is 0. Okay, 0. And then we need to calculate distribution factor for each. Okay, each n starts by BA. Okay, starts by BA. It is 0.75 divided by total 0.75 plus 1.6. Okay, because it is member stiffness divided by joint stiffness. So joint stiffness, we must total BA plus BC. So BA is 0.75 plus 1.6. So we get 0.319. This is 0.319. Okay, 0.319. So we will get BC by 1 minus 0.319. So we get 0.681. 0.681. So we do the same for joint C. Member stiffness is 1.6 divided by total is 1.6 plus 1.333. It is member stiffness divided by joint stiffness. Joint stiffness means CB plus CD. CB plus CD is 1.6 plus 1.6 plus 1.333. So that is joint stiffness. Member stiffness 1.6. So it is 1.6 divided by total 1.6 plus 1.333. So we get 0.546. 0.546. 546 minus 1. Okay, we get another one is 0.454. As long as, okay, we check the total must be 1, because 0.454 when we use 1.333 divide by 1.6 plus 1.333, we will also get 0.454, because this total must be equal to 1. This total also must be equal to 1. Okay, at each joint, distribution factor must get 1. At each joint, distribution factor must get 1 except and fixed. Except and fixed. Okay? Okay, now is the fixed end moment. Okay, now we want to put the fixed end moment into this fixed end moment, the moment that we have calculated, and we have considered both effect, external loading and support settlement. Okay, FEM for AB. Okay, I want to use this. Okay, it is negative. AB is negative 1312.5. Negative 1312.5. Negative 1312.5. And then for BC is 1617.5. 1617.5. And CB is 1742.5. Okay, like this. Okay, FEM. Then we can start distribution. We can start distribution. Okay, we can start distribution. Okay. Okay, start distribution. Remember, when we want to distribute, we must find the joint moment, and joint moment is opposite with member and moment. And the joint moment, we must times with distribution factor. Okay, we do it one by one. Okay, joint moment for A. It is positive. It is positive 1312 times 1. 1 is the distribution factor. Okay, FEM is the first member and moment in the table. and joint moment is opposite. So the moment that we distribute is not negative 1312, but opposite with this is positive 1312.5. So it is 1312.5 times 1, so we get positive 1, positive, we get positive 1312.5. 1312.5. Okay, next. Okay, total moment at B. Total moment at B, it is, okay, negative 1312. Opposite is positive 1312.5. Okay, so 1617.5. Opposite, negative 1617.5. Okay, we get negative 305. We get negative 305. We need to times with distribution factor 0.319 times 0.319. So it is negative 97.295. Wait. Okay, it is 97.295. 295. Negative 97.295. Okay. Again, okay, 1312.5. Okay, minus 1617.5. 17.5 times with 0.681. So it is negative 207.705. Okay, total of this 1, 2, 3, 4. Okay, must equal to 1. Must equal to 0. Must equal to 0. So check, negative 1312.5 plus 1617.5 minus 97.295 minus 207.705. It should be 0. Okay, it should be 0. The process, the actual process is actually like this. The actual process is actually like this. Okay. Okay, at joint B, this is joint B. This is joint B. We distribute joint moment. We distribute joint moment. We get moment, we get joint moment from N moment. So we have AB and BC. Okay, the member N moment we get from fixed N moment for AB, for BA is negative 1312.5. It is negative, okay, 1312.5. Get negative. And the moment, the other one is 1617.5. Positive 1617.5. And 1617.5 is positive. Okay, this is 1617.5. Okay, 1617.5. Okay, and these two, okay, is actually member and moment. And the moment that we distribute is joint moment. The member that we distribute is joint moment. So joint moment is opposite. So opposite, okay, this is opposite. Opposite, this is opposite. Okay, the blue is opposite. Okay, same value. Same value. So which value that we distribute? We distribute the blue. Okay, the blue arrow. So the blue arrow is equal to, okay, so the joint moment is equal to, by looking at the blue direction, blue arrow. So it is negative, a positive 1312.5, okay, minus 1617.5. So this total we times with distribution factor. We need to time with distribution factor. And the distribution factor is 0.3, 0.319. 0.319. So we time with 0.319. So that is why we get the value as negative 97.295. Okay, negative 97.295. Okay, so we continue to join C. Join C. The joint moment is negative 1742. Because 1742 is member and moment. Joint moment is opposite. So the value that we distribute is negative. Negative 1742.5 times with the factor. The distribution factor is 0.546. So it is negative 1742.5 times 0.546. So we get 951 negative. It is negative 9, negative 9, 5, 1.405. Okay, and 1742.5 times with 0.454, we get negative also 791.095. Okay, 095. So total must be equal to 0. So we get 1742.5 minus 951.405 minus 791.095. So we get 0. Okay, that is distribution. Okay, this is also 0. Okay, negative 1312.5 and 1312.5 is also 0. So next, after distribution is carry over. So it is carry over. So carry over the value. Okay, we must okay, find the value. Okay, by times this value with the factor. Okay, and the factor is 0 for n pin or n roller, and the rest is 0.5. Only n pin and roller, the factor is 0. Okay, so what we need to do is we have to bring value to the opposite. Okay, like this. Okay, carry value. So negative, not negative, 1312. This 1312 we have to times with 0.5. Okay, 0.5. A to B. Okay, to A only 0. The factor for A, B is 0. The factor for BA is 0.5. BC is also 0.5. This is 0.5. This is 0.5. This is 0.5. Okay, only one factor is 0. Only AB factor is 0. Okay. Okay. So it is 0, 0.5, 0.5, 0.5, 0.5, 0.5. Only A is 0. So the value that we carry over is 0 for AB. So the rest we have to times by 2, times by 0.5. So it is 1312.5 divided by 2. So we get 656.25. Okay, and then move to 207.705. 207.205 divided by 2. So we get 10 it is negative 103.6025. Okay, 951.405 divided by 2. So we get negative 4, bukan 9. Okay, 475.7 point. Okay, 0.7. Okay, 7025.7. Okay, 7025. Okay, there is 4 decimal places. 7025. 7025. Okay, 7025. And then we have 791.095. Okay, the last value here. It is 791.095 divide by 2 times 0.5. It is negative 395.5475. 5475. Okay, so this is the process distribution carry over, and after this we need to repeat the process again for distribution. Okay, for distribution, and then repeat for carry over, and then repeat for distribution, and then repeat for carry over, and then repeat for distribution. Okay, until the last distribution. Wait. Okay, until the last distribution reaches 0.0. Okay, so I want to shorten this by doing this in Excel. Okay, by doing this in Excel so that we can get the last value, the last distribution easily. So I will open Excel now. Okay. We wait for the Excel to be open. Wait for the Excel to be open. Where is it? Okay, this. Okay, so we have AB, BA, BC, CB, CD, DC, 6. Okay, we have DF. It is 1. It is 0. It is 0. Get the value. 319. 319. So this is 1 minus 0.319. And another one is 0.545. Check balik. 546. 546. 546. So this is 1 minus 0.546. Okay, for the FEM as the first member and moment in the table, so we have negative 1312.5 is negative 1312.5. Okay, negative, it is same, negative 1312.5. And then for BC we get 1617.5, 1617.5, and CB is 1742.5. 1742.5. Okay, 1742.5. There's no FEM for CD, okay, and DC. Okay, start with distribution. Okay, carry over. So for distribution, total moment, we put negative to represent the opposite condition of joint moment. So times with factor. The factor is 1. So we get 1312.5. Okay, total moment is 1312.5 plus 1617.5 times with factor 0.319. Okay, I log the distribution factor like this. Okay, and then again repeat the process. Joint moment is total, so plus this, okay, times with factor 0.681. Okay, I want to log the distribution factor. Okay, log like this. Okay, again, so it is total plus this. Okay, why zero value I still consider in the formula? Because we want to carry the formula, okay, for the next cycle. So times with the factor 0.546. Okay, I want to log the distribution factor. Okay, and then again plus 0 times with distribution factor. I also want to log this. Okay, this is 0 because the factor is 0. If there is the value, also get 0 because the factor is 0. For A, it is different because the factor is 1. The factor is 1 and we have FEM here, so we have to find the joint moment time with factor, so we get positive 1312.5. Okay, so for the carryover, this is equal to, okay, times with 0. So we get 0. So the rest we time with 0.5. Divide by 2. This is divide by 2. Divide by 2. Divide by 2. Cross opposite. Okay, so then check 1312.97.295 295, then 207.705 207.705 951 951.405, and then 791.095. Okay, and then the carryover check. Okay, 656.25 656.25, and then 475. It is 475.703 025 actually. So I actually set up to 3 decimal point in Excel. Okay, and then 103. Okay, 103. Okay, this is 103.85. 103. 207.705. It is 207.0 point this. Oh, wait. Okay. Okay, we have to check back with this. So this is 951.405, 951.405. Okay, I want to put the color, okay, for each element, different color for different element. Different color for different element. This is green and this is blue. So cross means, okay, cross here, cross here. Okay, so 1312.5 is divided by 2 is 656.25. 656.25 we get here. Okay, and then okay, so 97.295 we get 0 because of the factor. And then 207.705, it is 207.705. We divide by 2. We divide by 2. This divide by 2, we get 103.853. Okay, we check back. Okay, 8. It is 207.705. We divide by 2. So we get 8525. 103.8525. 103. Okay, the decimal places is wrong. 103.8525. This is 8525. Okay, 951.405 divided by 2, we get 475.7025. So this one, okay, 951.405 divided by 2 or times 0.5, we get 475.7025. Okay, and 791.095 divided by 2, we get 395.5475. 54775. Okay, then this is correct. Okay, so then I just need to copy and paste. Okay, you can also do the same, okay, on your own. Repeat again, paste. Okay, repeat one more time. Okay, we repeat one more time, copy and repeat one more time. Okay, repeat one more time, paste again, we get 0.14, 0.0. Okay, so from this table we get from Excel. Okay, this is second cycle, this is the third cycle. Okay, this is the fourth cycle. Okay, 5. Okay, 6 cycle. So if you do it manually, you have to repeat the process again and again. Okay, so until last distribution. So the last carryover, I just want to delete here. Okay, because the last value I want to okay, in order to find the total moment, the last must be distribution. Okay, if I want to set decimal places, okay, set decimal places maybe up to only 2. Okay, also can. 3 also can. We get like this. Okay. Okay, so all this 3. Okay. Don't write zero value in the table. So just delete the zero value. Okay. So from the table, so we get the end moment easily because we have set the formula. Under distribution and carry over, and then we just need to copy and paste, and then we drag until last distribution, where the last distribution equal to 0.0 something. We may stop. So okay, until the last distribution get 0.0 like this, and we find the total moment start from FEM in the table, and we find like this. So this value I will put, okay, in the table. So this is actually end moment. So the value is 0. Okay, wait for a while. Okay, wait So hang already. Okay, wait again. Okay, so assuming that all the value in the table has been transformed into this table. So lastly, we find the total moment. So end moment is equal to this. Okay, so MAB is equal to 0, MBA is negative 827, MBC is positive 827, MCB is 708.37, MCD is negative 708.37, and MDC is equal to negative 354.2. Negative 354.2. Okay, so now I want to continue to analyze this moment value. I want to use static equilibrium in order to determine the reaction at the support. So this end moment, as I said just now, is referring to M. This is referring to MAB. Okay, this is referring to MBA, MBC, MCB, MCD, MDC. Okay, so we will use this moment. Actually, from this value we can directly draw the bending moment diagram, because this is actually the internal moment. This is internal moment. This is internal moment. So having this, we can actually draw the BMD directly without shear force diagram. Except for the maximum moment, we need to draw by we need to identify the moment by finding the area in the shear force diagram. Okay, if we want to draw the moment, the bending moment diagram directly, so what we get? Okay, what we get? So we have three members or three elements. We have three elements. We have three elements AB, BC, C, CD. Okay, CD. I want to draw the shortest, okay, the shortest way to draw the BMD, in beam using the moment that we get from table. Okay, the moment that we get from table. Okay, I do it one by one element, and now we the first step is we have to focus to the sign, the moment sign for each end. Okay, at AB 0 doesn't matter. At MBA is negative sign. MBA is negative sign, so we put moment negative in the diagram. Moment negative. Okay, MBC, the moment is positive. MCB, the moment is also positive. MCD, the moment is negative. MDC, the moment is negative. Okay, so this is representing the moment, the sign. Okay, the moment that we get from the table. So from this, we can actually identify the position. Okay, the position of moment value. Okay, it shows where is the position. It is like this. Okay, so the negative 8 to 7 position will be located here. And what we need to do, we just, and the moment at A is equal to 0. So we will get the bending moment diagram for member AB as this. Okay. So this is the bending moment diagram. Okay. Okay, the position to represent positive 8 to 7. Okay, by just looking at the arrow, so we know that the point is located here. And for MCB is 708.37, the position of the moment. Okay, by looking at the arrow, the position is located here. Okay, we put the position of moment from the arrow. We identify from the arrow, from the moment direction. Okay, so that is the point. That is the point. But since member BC has UDL, we know that it is curved line. So we have to identify the whether this beam has maximum moment from shear force diagram. Okay, I will show it later on. Okay, we move to MCD MDC member, the last member CD. By using the moment direction, we can identify directly the position in the bending moment diagram, and the position is this. Okay, and another one will be So I just need to join, because there's no point load or UDL on a long member CD, so we just need to join this. Okay, like this, and then just join these two dots. Okay, so this is positive, this is positive, this is negative. Okay, now we want to identify the salient point in the bending moment diagram for member BC. So what we need to do is we need to consider member BC only, because we want the salient point in the bending moment diagram. Okay, actually we can analyze one by one member to identify the shear, the reaction at the support, the vertical reaction at the support. Okay, but since now is almost the 1.5 hour session, so I just jump to bending moment diagram. We draw directly from the moment that we got in the table, and I just want to focus on how we can identify the salient point in the bending moment diagram using shear force diagram. Okay, so we just need to consider the member BC only, since member AB and member CD has no point load, has no UDL, so we can skip that one for this example. Okay, so consider member BC only. So member BC has UDL. So I draw the diagram. BC has UDL. Okay, BC has UDL. Okay, I need to move this first. UDL. Okay, UDL, and since this is internal member, so we need to draw the free body diagram. So here, okay, this is B and C, right? This is B and C. So this is CY1 actually, and BY2. This is BY2. Okay, so the loading is 30, right? 30. Okay, refer back to the question. It is 30 and 5. 30 and 5. Okay, and apply the moment that we get from table. Okay, so same with this direction. Okay, because we analyze this. Okay, the free body diagram for member BC only. So the moment is 827. This is 827 and 708.37. 708.37. Okay, we have BY and CY. Doesn't matter, we just label like this. Okay, the original value is actually BY1. We have AY1, we have AY, we have BY1, BY2, we have CY1, CY2, and DY. So all this explanation is actually under topic slope deflection method. How we actually draw the free body diagram of each element in the beam or in the frame. Okay, so this is the structure. It is just like simply supported beam. So we use static equilibrium to identify BY and CY value. So we will get the shear force diagram for this member, then from this shear force diagram we can identify the maximum moment and in the bending moment diagram for member BC. Okay, so by taking moment at T equal to 0, so we get 827, okay, plus 708.37, okay, plus 5 by minus 30 times 5 times 2.5 equal to 0. Okay, so what we get is 827, we plus with 708.37, we minus by 30 times 5 times 2.5, okay, we divide by 5, we get by. Okay, we get by. So by is equal to, okay, wait for a while. Okay, Assalamualaikum. So coming back to this. Okay, sorry for take long. Okay, break because of the urgent meeting just now. So now we actually I want actually to show to you how we want to draw the the bending moment diagram with salient point for member BC. This is actually the bending moment diagram. So okay, we draw this based on the end moment that we get from table, from distribution table. Okay, and the position of the bending moment diagram. Okay, the value, for example, this is negative 827. So how we get this 827 here is based on the sign direction, the moment direction. So this is actually 827. So this is 827. This is 708.37. 708.37, and this is 354.2. So by analyzing shear force diagram for member BC only, since member BC only has UDL, so we can analyze beam BC as just like we analyze simply supported beam. Okay, simply supported beam. So it is like this. So we get BY. Now we can calculate BY as 827 plus 708.37 minus 30 times 5 times 2.5 divide by 5. So we get BY as 232. As 232.074 kilonewton. So we will get 30 times 5. Okay, it is 30 times 5 minus 232.074. So we get BY as 232. This is 232.074. So we will get CY as negative 82.074. Okay, so the shear force diagram by considering this shear value is like this. Okay, so it is the T is 232.074. This is 82.074. Then we can draw the shear force diagram. Okay, the shear force diagram. So it is like this. So it's going up. Okay, going up to 32.074. We minus by 150, so we get 82 here. Okay, and then we get is 82. Okay, so this is actually 232.074, and this is 82.074. 7. This is 7. Okay, this is positive. Means that this is trapezium. What does it mean? Trapezium means no maximum moment in bending moment diagram. Bending moment diagram. Okay, and since this is 5 meter, so the area of this is equal to 1/2 times area of shear force diagram equal to 1/2 times 232.074 plus 82.074 times 5. So this we get 232.074 plus 82.074 A times 5 divided by 2. So we get 785.37. Okay, so since it is trapezium, so we will get, okay, so actually in order to check the value, this value, okay, this 7, the area of shear force diagram, is 785.37. the area, this is the area of shear force diagram for BC. Okay, so it is okay, so we just need to join. We have to join this as this. Okay, so when we combine this, we will get the diagram. We combine this diagram. Okay, we combine this diagram, so we get like this. Okay, this is okay. Okay. And this. Okay, so the shear force diagram, when we combine, actually element by element also okay, but if we want to combine, we get this. We will get because of UDL, so and no maximum moment because the shear force diagram is trapezium, so we just get like Okay, this is the shear force diagram. Okay, this is positive, this is negative. Okay, so the value is 827 here, and 708.37, 708.37, and B 300 and 354.2. 354.2 kilonewton meter, kilonewton meter, kilonewton. Okay, so this is the bending moment diagram, for frame, for beam that we actually analyze. Okay, considering support settlement. Okay, so that's all for this video. Inshallah, I will make another video to analyze another beam question. Okay, which is the pre-assignment, the pre-assignment question. So that's all for today. Okay, for this video, not today, for this video. Okay, inshallah we will meet again. Assalamualaikum warahmatullahi wabarakatuh. Bye bye.